Welcome to lecture series on heterocyclic chemistry. In this lecture, we are going to discuss about the chemistry of indole. We will see the various methods for the preparations of indole, as well as we will discuss various reactions of indole, including aromatic electrophilic substitution reactions. Now, before starting to discuss the various methods for the indole synthesis, let us understand the significance of indole in natural product chemistry. There is a class of natural products called as alkaloids containing the nitrogen in the form of some heterocyclic moiety. There are range of alkaloids which contains indole as a substructural unit. Some of the examples are shown here: tryptamine, strychnine, lysergic acid, trizerpine, and halocyanuric alkaloids. These are the only representative examples. There is a wide range of alkaloids which contain indole as a substructural unit. These alkaloids also show certain physiological activities. For example, strychnine is a poisonous plant, whereas trizerpine is useful in the treatment of hypertension. So from this chart, it is very sure that alkaloid indole is a very important heterocycle as far as the alkaloids are concerned. As far as the biosynthesis of all these alkaloids is concerned, it is obtained from an essential amino acid called as tryptophan. Tryptophan is a biogenetic precursor for the synthesis of many alkaloids containing indole as a substructure unit. And tryptophan again contains indole as a substructure unit. Now, apart from alkaloids, there are again some other molecules naturally occurring which contain indole as a substructure unit. We have already seen the utility of L-tryptophan in the biogenesis of alkaloids. Another one is a serotonin, which is acting as a neurotransmitter. Third one is a melatonin, which is acting as a neurohormone. Again, the biosynthesis of serotonin as well as melatonin starts from the L-tryptophan. Now, another interesting and important class of naturally occurring alkaloid is indole 3-acetic acid. It is abundant in the plants and it acts as a phytohormone. Now, apart from these natural products, there is a very historic example called as indigo dye. In fact, the chemistry of indole initiated with the development of indigo dye chemistry, indigo dye industries. Indigo dye contains again indole as a substructure unit. From indigo, Adolf Baer has prepared indole by converting indigo into isatin. Isatin was converted to oxindole, and oxindole on zinc reduction forms here indole. So indigo is a very important molecule as far as the historic significance is concerned. Now, natural products. Apart from the natural products, again indole is a very abundant substructure unit in range of commercially available drugs. For example, ondansetron as well as indomethacins. Only these two representative examples are shown. There are range of drugs which contain indole as a substructure unit. Ondansetron act as an anti-nausea, and because of the ondansetron, it is possible to take the higher doses of the anti-tumor compounds, that is for use in cancer therapy. The indomethacin is acting as a non-steroidal anti-inflammatory drug. Now, from these two slides, it is very sure that indole is very abundant in the natural products as well as available in range of drugs molecules, and therefore it is necessary to understand the chemistry of indole. Now, owing to the great biological significance of indole, various methods for the synthesis of indoles have been developed. There are hundreds and hundreds of methodology of indoles. Here, some of the name reactions we have listed, 9 name reactions we have listed, and we are going to discuss these 9 methodologies. These 9 methodologies are very popular methodologies, and generally they are documented in the standard textbooks of heterocyclic chemistry. So we'll divide our lecture series on the methods of indole synthesis in 3 parts. Part 1 will be related to the first 5 reactions. Part 2 will be related to these 3 name reactions, and the part 3 will be dedicated to the Fischer indole synthesis, which is a very popular and the preferred method for the preparations of indole. Now, this is a summary, or we can say the chart of various demonstrating the various methods of the indole synthesis. Now, these are the Reissert indole, Madelung, Bischler, Nenejescu, Batcho-Leimgruber, Bartoli, Gassman, Fischer, Larock, and this is a modern methods for the synthesis of indole using cross-coupling reactions. Now, in this chart, one thing is very common, that we have to start with the appropriately substrate benzene rings. In these 3 cases, substrate benzene ring again is a substrate benzene ring. We have to start with the substrate benzene, and we have to make only efforts to construct this spiral ring here. So Most of the methods for the synthesis of indole starts with the appropriately substrate benzene ring. It may be a monosubstrate or it can be disubstrate. It can be disubstrate like this. And then we reach to the indole synthesis. So here we have to make a arrangement for the constructions of this spiral nucleus. Now in this particular lecture, we are going to discuss these 5 name reactions: Reissert indole synthesis, Batcho-Leimgruber indole synthesis, Madelung indole synthesis, Reissert indole synthesis, and Bichler indole synthesis. Now before starting for the actual synthesis of indoles, let us have a look on the strategy or the retrosynthesis analysis of indole. Now in maximum methods available in the literature for indole synthesis, we have to make an effort to construct this spiral nucleus. This spiral nucleus can be prepared by the dehydration of these two alcohols 1 and 2, and if you do some retrosynthetic analysis of 1 and 2, then we reach to here monosubstrate benzene, that's aniline. It's a disubstrate benzene, that's a toluidine type of the substrate. And once this is decided, once this aromatic substrate decided, then we have to make an arrangement of appropriate substrates offering. Here is a 1 number carbon atom, it is offering 2 number of carbon atoms to construct this spiral nucleus. So aniline on reactions with the alpha haloketone is a doubly electrophilic building block leads to form indole. Similarly, acid chlorides or halides on reactions with the orthotoluidine leads to here formations of the indole. Now another way of looking at the indole synthesis strategy, is to construct this 5-membered ring. Here the carbon, nitrogen, this we have to work on this particular portion of this indole molecule, and one can start with the monosubstrate benzene, another can start with the disubstrate benzene. Here one can start again with the disubstrate benzene, and here we can start with the benzene, or this strategy you can employ for dipolar cycloaddition reactions of the benzene. Now, in the synthesis of indole, we'll come across a carbon-carbon bond forming reactions. We'll come across a Friedel-Crafts variety, that is a carbon-carbon bond forming reactions, and another one is a carbon-nitrogen bond formations. So, if we are good at the fundamentals of carbon-carbon bond as well as a Friedel-Crafts variety as well as a carbon-nitrogen bond forming reactions, then it is very easy to understand the synthesis of indole. As far as the carbon-carbon bond is concerned, we'll come across some aldol-related variety of the carbon-carbon bond. And in some of the cases, we will come across sigmatropic processes like 3,3 sigmatropic rearrangement, where the carbon-carbon bond will be constructed here with the help of pericyclic reactions. Then carbon-nitrogen bond is a carbon heteroatom bond formation, is a last step generally in the synthesis of indole. And this cyclization is generally a 5-exo trick. Here the 5-membered ring is formed by attacking of the nitrogen on the trigonal carbon atom, and most of the time whatever the double bond is there on the trigonal carbon atom, then it is opening at the outside, therefore it will be described as a 5-exo trick cyclization according to the Baldwin nomenclature. Now here we have made some list of the substrates which are generally used in the synthesis of indole. One is here NN-dimethyl or dialkyl, it's a amide, formamide, it's dimethyl acetal. NN-dimethyl, for example, R is equal to methyl, uh, DMF dimethyl acetal, acid halide, alpha haloketone, diethyl oxalate. So if you look at all these cases, they are found to be doubly electrophilic building blocks. Here chloride is a very good leaving group, it is also a very good leaving group. So at the same carbon atom we are having two electrophilic center here. If it is in this case, the electrophilic centers are at 1 and 2 positions. Halogen is a very good leaving group, it's also a very good leaving group, so it's a doubly electrophilic building block. This is also a doubly electrophilic building block at 1 and 2 positions, or one can have a again doubly electrophilic center at the same carbon atom. So if this doubly electrophilic building block is treated with a doubly nucleophilic building block, then one can get here the synthesis of indole. Here the two doubly nucleophilic building blocks are shown. Aniline we have seen shows plus R effect. So because of the plus R effect, this carbon atom is negative. Nitrogen lone pair, this is also nucleophilic in nature. So this is a doubly nucleophilic building block. This is a structure of enamine. Enamine is also doubly nucleophilic building block. So if you make a permutation and combinations of certain electrophilic building block with the doubly nucleophilic or nucleophilic building block, then one can reach to the indole nucleus. So One should be very good in understanding the reactivity of the substrates. Then and only then one will be it will be very easy to understand the mechanism of the process involved in the indole synthesis. So with this background, let us start for the first methodology for the synthesis of indole. It is called as a Reissert indole synthesis, reported in the year 1897. Reissert indole synthesis involves a condensation base catalyzed condensations of orthonitrotoluene with diethyl oxalate. In presence of base, it generates a carbanion. This carbanion is stabilized by minus R effect of the NO2, and we get here a carbon-carbon bond forming reactions. And its name is ethyl orthonitrophenyl pyruvate. This orthonitrophenyl pyruvate on hydrolysis gives carboxylic acid, and if it is subjected to reductions with zinc acetic acid, NO2 group will be reduced to NH2, and as soon as it is reduced, it will undergo cyclization. That's a 5-exoteric cyclization leading to form indole 2 carboxylic acid. And indole 2 carboxylic acid can be converted to indole. In fact, Reissert has done this transformation by heating to indole to carboxylic acid under mineral acid at very high temperatures, leading to form here indole. So in this way, in Reissert synthesis, we have seen the condensations of orthonitrotoluene with diethyl oxalate. Diethyl oxalate is offering only one carbon atom. It's a doubly electrophilic carbon atom, and here's a carbon-carbon bond and the carbon-nitrogen bond. Let us see the mechanism of this reaction. The mechanism of these reactions involve a carbon-carbon bond reaction here. This is a aldol-related process, base catalyzed condensation here. In presence of a base, this hydrogen is abstracted and we get a resonance stabilized carbon, and because of the minus R effect of NO2, then it attacks on carbonyl carbon atom and we get a nucleophilic substitution at sp2 carbon to get a alpha ketoester with the nitro group at the ortho position. On hydrolysis, this ester is converted into carboxylic acid. Under reductive condition, zinc acetic acid NO2 is reduced to the NH2, and NH2 attacks on carbonyl carbon atom. We get a 5-exoteric cyclization to form this compound, and later on dehydration occurs and we get a indole 2 carboxylic acid. So this is a very simple mechanism of the Reissert indole synthesis. A carbon-carbon bond is formed by aldol-related process involving carbanion, and the carbon-nitrogen bond is formed by the reductive cyclization. NO2 group is reduced to NH2, and then it attacks on carbonyl carbon atom to form a cyclic system here. Now let us see the synthetic utility of this Reissert indole synthesis. In Reissert indole synthesis, diethyl oxalate is a common substrate offering one carbon atom at the end here. This is coming from diethyl oxalate. This is also coming from diethyl oxalate. And then only variation that one can do is in the aromatic substrate. Instead of orthonitrotoluene, one can take a substrate orthonitrotoluene like this. Here the methoxy group and the methyl group are tolerated under the reaction conditions. Here cyclization occurs. This NH2 group can also attack on carbonyl carbon atom to get a quinolone derivative, 2-quinolone derivative, but the yield of this reaction is yield of this side product is very less. This methodology can be extended to the synthesis of azaindole. Instead of taking nitrotoluene, one can take a picoline nitro compounds, 4 picoline nitro compounds, and this is more acidic in nature compared to the nitropicoline. So under basic conditions, we get again carbon-carbon bond, and reductive cyclations offers here azaindole. The yield of this methodology is relatively high because of the more acidity of these CH3 groups. So in this way, the first methodology we have discussed, we have completed. That's the Reissert indole synthesis. Now let us discuss another methodology called as Batcho-Leimgruber indole synthesis, reported in the year 1971. In Reissert indole synthesis, one of the substrate was diethyl oxalate. Now instead of diethyl oxalate, now we are starting with here formamide acetals. Amide and its acetal, that's a formamide acetal. It is offering only one carbon atom. Now in presence of a base like pyrrolidine, this will abstract a proton and it will undergo now condensation to form here enamine here. A nitrostyrene will be formed, and this nitrostyrene on reduction undergo reductive cyclizations to form the indole molecule. So instead of diethyl oxalate, Batcho-Leimgruber utilized formamide acetal as the one carbon atom source. Here we have to manage only one carbon atom to form a carbon-carbon bond and the carbon nitrogen. Now let us see the mechanism how it proceeds. In presence of a base, we will get here a in system here, and this in of orthonitrotoluene will react on a electrophilic molecule, it's a iminium ion, and we get here a carbon-carbon bond forming reactions. So we got here carbon-carbon bond forming reactions, and then it departs, methoxy group departs, and we get here trans dimethyl amino 2 nitrostyrene. This amino compound, enamine compound on reductions forms here NH2, and NH2 undergo attacks on enamine, we get the cyclizations, and finally dimethylamine is eliminated to get the indole derivative. Now in Batcho-Leimgruber indole synthesis, this is compulsory. N,N-dimethyl formamide acetal is compulsory substrate here. The other substrate that can be varied is a orthonitrotoluene. Here some substituents are shown. Benzyl here, this phenolic group is protected here. Methoxy group is a ester. All of them are transformed into indole in a very good yield, 70% yield, 76% yield, 73% yield. So in all the cases, the first step is the formations of the styrene derivative. It's an enamine derivative, and this enamine derivative under reduction forms your indole derivative. Here, in presence of nickel, NH2, NH2 liberates here H2 here, N2 molecule is converted to hydrogen, active hydrogen, and reduction occurs. So in this way, we have seen the Batcho-Leimgruber indole synthesis invented in the year 1971. Now there are important similarities between the Reissert indole synthesis as well as Batcho-Leimgruber indole synthesis. In the Reissert synthesis, diethyl oxalate was required, whereas in Leimgruber indole synthesis, N,N-dimethyl formamide acetal is required. That is offering in both the cases, it is offering one carbon atom, and there is the same starting material, let's say orthonitrotoluene, and then reactive cyclization is required for both the methodologies. There was a orthonitro pyruvate ester, here is a orthonitro-enamine type of the compound, nitrostyrene type of the compound, and then after reductions it undergoes cyclization. So this similarity has to be observed very carefully as far as the Reissert synthesis and the Batcho-Leimgruber indole synthesis is concerned. Now let us discuss the third methodology, that is a Madelung synthesis reported in the year 1912. This methodology involves a base catalyzed condensation of orthoalkyl anylides. This is a anylides, and it can be obtained from acid chlorides. So instead of orthonitrotoluene that we have seen in previous two cases, one can start with the orthotoluidine on reactions with the acid chlorides. We will get here orthoalkyl anylides. Orthoalkyl anylides under basic conditions at very high temperature forms here two substrate indole molecule. Now this is a very good methodology, but the serious drawback is about the strong base. We require sometimes one more than one equivalent of the base sodamide or potassium terpetoxide, and very high temperature from 250 to 350, and even in some cases it is up to 400 degrees centigrade. So in this case, orthoalkyl anylides on basic conditions undergo cyclization, and it is called as a Madelung synthesis. Let us see the mechanism of this reaction. Now this orthoalkyl group, orthoalkyl anilide is the general name of this substrate. This orthoalkyl group is not acidic in nature. It is not fairly acidic in nature, and therefore we require a very strong basic conditions, like strong base is required here, and then in presence of a base it generates a carbanion, and this carbanion attacks on carbon atom. Here we get a carbon carbon bond forming reactions. It can be described as a 5-exo trick because 5-membered ring is formed. This carbonyl group is opening at the outside, and there is a exo, and it is attacking on the trigonal carbon atom. Therefore, it's a 5-exo trick cyclization according to Baldwin nomenclature. Then under acidic condition, this will become OH, and this will undergo dehydration to form the substrate indole. So the mechanism of Madelung synthesis is very straightforward. Now here some of the examples are shown. We are getting two substrate indole. Here unsubstrate indole is possible to prepare in 68%. It's the original work of Madelung, where the 270 to 300 degree temperature, 310 degree temperature was employed. Here also 200 degree temperature, here is a 360 degree temperature. So we got the here indole in relatively good yield also, 68%, 67% yield of the indole. But the high temperature and the strong basic condition, this is definitely a very important drawback of Madelung synthesis. Now, with the advent of some modern bases like N-butyl lithium, N-butyl lithium is also a strong base. So N-butyl lithium can be utilized in Madelung synthesis, and if you replace sodamide or potassium butoxide with N-butyl lithium, it is possible to perform Madelung synthesis at very low temperature, 20 degrees centigrade and 15 degrees centigrade. In previous cases, the 200 to 400 degrees centigrade temperature was required, but here, because of the n-butyl lithium, it is possible to perform Madelung synthesis under very mild conditions. In this case, we get here 2-phenyl indole, and it's also the 2-phenyl indole derivative. Now, apart from replacement of n-butyl lithium, replacement of sodamide by n-butyl lithium, one can also modify the substrate in Madelung synthesis. In Madelung synthesis, we have seen that this methyl group or the alkyl group is not more acidic in nature. But if suppose some electron withdrawing groups are attached like cyanide, here is a ester, here is a sulfone, then in presence of potassium butoxide, it is possible to perform Madelung synthesis at again room temperature. The yield of the reactions are excellent here, 79%, 79, 81, 90%, and again 74, 83%. So Madelung synthesis becomes a very successful synthesis if we are having this acidic carbon atom here, and for that, if there is an electron withdrawing group attached, then in that case the Madelung synthesis is a very good methodology to prepare the indole molecule. Now here is a combination of the two methodology. One is a Madelung synthesis original and another one is a Wittig reactions. Here the Wittig reagent is formed, phosphonium salt is formed. This is a benzyl bromide. It undergo SN2 displacement. We get a phosphonium salt. Then under zinc acetic acid conditions, it is converted to NH2, and NH2 is acylated here, and we get here anilide derivative. And this anilide derivative with the phosphonium salt, part of the same molecule, undergo intramolecular Wittig reaction. This is intramolecular Wittig reactions with the amide is reported here, and the yield of this indole derivative was found to be the 88%. It is called as a Wittig Madelung indole synthesis. So in this way, we have learned the another third methodology for the synthesis of indole, starting from orthoanilide in presence of a very strong base to form the indole derivative. Now let us switch over to the next method, that's a Bissler indole synthesis. In Bissler indole synthesis starts with the monosubstrate benzene, that's aniline. It is treated with the double electrophilic building block. We get here alpha aryl. This is alpha aryl amino. This is aryl amino ketone, and this under acidic conditions undergo intramolecular Friedel-Crafts type of the variety, and we get a here indole molecule. Now mechanism here is a SN2 displacement. We get here this is alpha aryl amino ketone. This alpha aryl amino ketone under acidic conditions undergo aromatic electrophilic substitutions. We get here a cyclization sigma complex, and then sigma complex here preserves its aromaticity, and later on dehydration occurs and we get a here indole molecule. So in Bissler indole synthesis, two bonds are formed. One is a carbon-carbon, it is through the Friedel-Crafts, and a carbon-nitrogen is through the SN2 displacement. The reactions of a nucleophilic nitrogen with the electrophilic carbon atom here. Now, if this alpha haloketone is not symmetric, then we get a mixture of the products due to the rearrangement reactions, some rearrangement reactions, and therefore this Bissler indole synthesis is sometimes not very popular compared to any other method, because it is restricted to the here we get a mixture of the products if this is not symmetrical. Now this problem is overcome by employing protected form of this aldehyde or a ketone here. It's a protected aldehyde here, alpha bromoaldehyde, and it's in the form of protected as acetal is here. Then in presence of trifluoroacetic anhydride triethylamine, it forms here a carbon nitrogen bond, and then under the conditions here, acidic condition, it opens, and then finally we get a indole molecule. The yield of this reaction is very high, and it's only due to the protections of this ketone. Polyphosphoric acid can be employed in the cyclization reactions, leading to form here 64% yield of this indole product. So in this way, we have learned the indole synthesis, where we have to start with the alpha haloketone and the aniline to form alpha aryl amino ketone. These under acidic conditions undergo cyclization to form the indole derivative. Now the last methodology for the indole synthesis is Nenescu indole synthesis. Nenescu indole synthesis involves a condensation of benzoquinone with enamine here. Benzoquinone on condensation with the enamine forms here 5-hydroxyindole. Similarly, if it is a substrate quinone, then we get a mixture of the products. Now this Nereuscu synthesis was reported in 1929, but it has got some importance in the 1950s or 60s when it was came to know that 5-hydroxyindole is a very common substitute in most of the natural products. Therefore, Nereuscu synthesis is a very important synthesis as far as the 5-substrate indoles are concerned. Let us see the mechanism of this reaction. Here it involves a carbon-carbon bond and a carbon-nitrogen bond forming reactions. The carbon-carbon bond forming reactions is a Michael type of the reaction. As a it's a Michael type of the reaction. It's a acceptor, it's a donor, and we get here a carbon-carbon bond. Then here nullification of positive charge on this imine occurs. Then this NH2 attacks on carbon atom, and later on aromatization occurs, leading to form here 5-nitro 5 5-hydroxy indole molecule. This is the mechanism. A tentative mechanism is shown as is given in the standard textbooks of organic chemistry, heterocyclic chemistry written by R.K. Pensel. Other mechanisms of Nereuscu indole synthesis also exist in the literature. Now let us see. So in this way, we have learned the 5 different methodologies for the synthesis of indole. We started with the orthonitro-toluene in both the cases and work on this another building block offering one carbon atom. Here is a diethyl oxalate. Here is a N,N-dimethyl formamide. In both the cases, a carbon-carbon bond forming reaction occurs and then NO2 group is reduced and under reductive cyclation occurs to form the indole derivative. This is a orthoalkyl anides can be prepared from again orthotoluidine and it requires a very strong basic conditions to form a carbon-carbon bond. In Bischler indole synthesis, we have to start with the alpha bromoketone, reacts with the aniline, and then it undergo Friedel-Crafts reactions, we get a indole derivative. The last one is an Nereuscu indole synthesis, enamine. It undergoes cyclocondensation to form the 5-hydroxyindole. So in this way, we have completed the 5 indole synthesis, and in all the cases, we have constructed this spiral nucleus starting from appropriately substrate benzene rings. Now, once this indole synthesis 5 name reactions we have covered, now it's time to check our progress, and therefore the students should undertake various problems for the indole chemistry. Now, one variety of the problem is predict the product of following reactions with suitable justifications. Here, this CS3 group secondary butyl lithium is employed, and diethyl oxalate. It means it's a Reissert indole synthesis. So it will abstract a proton from this CS3. It will become a carbon and diethyl oxalate, and then reductive cyclization will occur here. Sorry, this NH2 group is already here. So this nitrogen will attack, and one can easily write the product of this reaction. It is an example of Nereuscu indole synthesis. This is again an example of Reissert indole synthesis. Then this is a Madelung indole synthesis. Madelung Wittig reactions here. We have already discussed these reactions in the previous slides. And the last slide is related to the writing mechanism. Students should undertake the practice session for writing the various mechanism. This is for Nereuscu indole synthesis. This is for Madelung synthesis, and this is again for the Madelung synthesis. Students should write the mechanism of these 3 reactions in this way. So in this way, we have completed the 5 different methodologies for the synthesis of indole. In the next lecture, we will cover another 3 methods for the synthesis of indole. Thank you very much for watching the video. Thank you very much.